In the next few lectures, I am going to discuss the Lindstrom-Gesell-Vienno lemma, popularly known as the LGV lemma. This is a theorem which gives a combinatorial interpretation of determinants of matrices whose entries themselves have a certain combinatorial description. So before we go into the LGV lemma, let me just remind you what the determinant is. I'm sure all of you know this, but it doesn't hurt to have a quick review. So if we have a matrix M, which is an n by n matrix, so we'll write its entries as Mij. I and j go from 1 to n. Then the determinant of M is the sum over all permutations sigma in Sn of sine sigma times product I goes from 1 to m, mi sigma I. So this determinant is actually a signed sum. Some of these products appear with a positive sign and others appear with a negative sign. And what is this sign? Well, let's just recall what this sign is. It's the parity of the number of inversions of sigma. So you define the set of inversions of sigma to be the set of all pairs I comma j, where 1 is less than or equal to I, strictly less than j, less than or equal to n, but sigma I is greater than sigma j. So I is less than j, but sigma I is greater than sigma j. It's an inversion. And sine sigma is defined to be minus 1 raised to the number of inversions of sigma. Now, an important property of this sign that we will be using when we prove the LGV lemma is the following. If sigma prime is obtained from sigma by interchanging sigma I and sigma j for some I less than j, then the sign of sigma prime is the negative of the sign of sigma. Okay, I'll leave it to you as an exercise to try to prove this result from first principles, or you can look it up in any number of sources. Okay, so now let's come to the kind of motivational examples to which we will be applying the LGV lemma. And so these examples, somehow two of the most common examples go back to ancient Indian combinatorics. I will write down a few infinite matrices. So the first is called the Suci prastaara. This was introduced as a method to compute binomial coefficients by the Indian mathematician Pingala, who lived in about 200 BC, and it was a method for computing binomial coefficients. So Pingala said, start with a list of just ones. So the first row of this array, so the prastaara refers to an array, and so the first row of the array just consists of ones. Now each subsequent row of the array is a sequence of partial sums of the previous row. So the second row, the first partial sum of this 1, 1, 1 is 1. The second partial sum is 1 plus 1, so that's 2. The third partial sum is 3. The fourth partial sum is 4. So the second row is just 1, 2, 3, 4, 5, 6. Now the third row is going to be the sequence of partial sums of the second row. So 1 plus 2, that's 3. 1 plus 2 plus 3, that's 6. So here you're getting the triangular numbers. And the next row is going to be the sequence of partial sums of this previous row. So again you get 1, 4. So 1 plus 3 plus 6, that's 10. 1 plus 3 plus 6 plus 10 is 20. 1 plus 3 plus 6 plus 10 plus 20 plus 15 is 35, and so on. So here I think I'll get 56. And let's just do one or two more rows. 1, 5, 15, 35, 70, and I guess this is 126, and so on. So what you see here are the binomial coefficients. Aij is the binomial coefficient. So let's call this matrix A. It's an infinite matrix or an infinite array of integers. Its ijth entry is just the binomial coefficient I plus j, choose I. If you look along a row here, for example, you look at this diagonal 1, 3, 3, 1. These are the binomial coefficients. 3 choose 0, 3 choose 1, 3 choose 2, and so on. So the numbering here starts from I0. And formally this array can be defined by saying that Aij is sum k goes from 1 to j, ai minus 1 j for I greater than 1, with the base case a1 j equals 1 for all j greater than or equal to 1. So this is for all I greater than 1, greater than 0, j greater than, I think this should be j greater than or equal to 0, j greater than or equal to 0. And so that's the Suci prastaara of Pingala. And we'll be interested in determinants of this matrix. I'll just draw one more row here so that I get a nice interesting determinant. 21, 56, 126, and this will be 252, I guess. So we'll be interested in looking at minors of this matrix. So we may look at a minor like we choose some rows and some columns. So let's look at this submatrix where we choose rows. So the rows and columns here are numbered 0, 1, 2, 3, 4, 5. This is I, and j is 0, 1, 2, 3, 4, 5, and so on. So I'm choosing columns 1, 3, 4, and I'm choosing rows let's say 3, 4, and 5. So this is just a minor of this infinite matrix, and we can try to evaluate this minor, and it turns out that this determinant is 210 in this case. Well, this array, this Suci prastaara, has an amazing property that every minor of this matrix is positive. This is not at all clear. Just because the matrix has positive entries does not mean that its determinant is positive, because in the definition of the determinant there is this sign, and so it's it could be quite surprising that the determinants are positive, and in fact they are positive integers because all the entries are integers. So you could also ask, what does this determinant count? And this answer is given by the LGV lemma. Another interesting array, again coming from classical Indian combinatorics, is a variant of the of the Suci prastaara, and this is found in the work of Halayuda, though it may have been been discovered much before. So this is around 975 CE. He gave an alternative method for computing binomial coefficients. And here what you do is you start with 1 0 0 0, and then the next row you write 1. Now each term in the ith row is the sum of two terms in the I minus first row. So this here you will get by adding this and this. This is so for j greater than 0, for j equals 0, we just take a I0 is the same as a I minus 1 0, and this will just propagate a 1. So let me draw a few more terms here. And if you continue in this manner, you get and so on. Let's call this matrix B, and this is called the Meru prastaara. It's in the West, it's commonly known, well, also in India, it's commonly known as Pascal's triangle, and it wasn't really well known for a long time that these things have been studied in India for a very, very long time. So the Meru prastaara is defined by these equations. It's what people often call Pascal's triangle, and maybe I should call this B here, since this is a matrix B. And Bij is nothing but I choose j. So note that Bij is positive if and only if I is greater than j. This is a lower triangular array, and you can also look at minors of this array. For example, we could take something like this. So I've chosen, let me just number these rows and columns too. So these rows and columns are again numbered starting with 0. So you could take a determinant such as this and compute it, and again you will find that these determinants are always positive or 0. They are always non-negative, and in fact it's very easy to say when such a determinant is positive or negative. Come back to this in a moment. Let me just introduce one more array, and this is a Hankel, what is known as a Hankel matrix. So the Hankel matrix of Catalan numbers. We've met the Catalan numbers several times before in this course, and now we just arrange them into a matrix. So this matrix is again an infinite array: C0, C1, C1, C2, 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 C3, 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 and so on. So this is an infinite array. And it turns out that this array also has all minors positive. So let's look at a general setting. Let M equal to Mij, say I. Let's just take, since all these arrays here we're taking have indexing starting from 0, let's just take indexing starting from 0. Then given 0 less than or equal to alpha 1 less than alpha 2 less than alpha n. You could also take a finite array, in which case, so let's write it like this: an n by n array where we allow n to be infinity. So let's assume the array has at least one entry. So you take a finite set of integers alpha 1, alpha 2, alpha n, and another finite set of integers beta 1, beta 2, beta n. Then we denote by m alpha 1, alpha n, beta 1, beta n, the determinant of the minor of the submatrix, which is the determinant of a submatrix is called a minor, of the submatrix obtained from M by choosing row numbers alpha 1, alpha n, and column numbers beta 1, beta n. So in this example here, this determinant here is A of we have chosen row numbers 3, 4, 5, and we've chosen column numbers 1, 3, 4. And that is this minor. And we say that, so we will be using the LGV lemma to show that firstly, if we take the array associated to the Suci prastaara, then these minors are all strictly positive. For all alpha 1, alpha n, beta 1, beta n as above. And we will also show that if you take the Meru prastaara, B alpha 1, alpha n, beta 1, beta n, then this is greater than or equal to 0 for all alpha 1, alpha n, beta 1, beta n as above, and it is positive if and only if alpha 1 is greater than or equal to beta, alpha I is greater than or equal to beta I for I goes from 1 to n. And otherwise it's going to be 0. And we'll also see that certain minors of the Hankel matrix are positive, namely the minors obtained by taking the first few rows and columns, something like this. This minor will be positive. Another minor that will be positive is a minor of this kind, where you leave out the first row and first column, but you take a minor starting from the next row and column. Such minors will be positive. Actually, it will turn out that this matrix, Hankel matrix of Catalan numbers, also has all positive minors, But the LGV lemma will only allow us to prove it for these kinds of minors.